Welcome to Chemistry 111. Today we will finish Chapter 3. We'll start looking at the old tests. Because we're kind of on this hybrid classroom thing, I'll probably do, I've done online tests in the past, not a huge fan. What I'd like to do is something I've done in the past, and can give you a take-home test. Basically, when I hand this out, I'll send it to you via email, post it on somewhere or another, probably just send you via email, but you'll have like a week to do it. The basically walking through, it's going to be like, hey, you have you can work with other people, but you got to show your work, show your thought process, get full credit. If it's a mathematical problem, you got to show how you got the math. It's all well and good that you can punch it in your calculator and get it, but show how you got it to get the credit. Because the idea is, rather than try to, yes, it might be a little bit harder than, say, a multiple choice one, but rather than it's like, I'd rather you learn the process and be able to show how you do it. And even if it's you're learning it for the first time while you're looking at this problem, I want you to be able to kind of do it. And I think you learn more from a take-home test than you do from just a test I give you an hour, 2 hours to do a bunch of semi-multiple guesses, especially a problem that you don't know and it's not multiple choice. You either guess or leave blank. This, you got the time, you don't really have the excuse of leaving it blank. So I figure this will be a little bit more of a learning example. But I'll show you after this the multiple choice test that I gave last year, and also example of the take-home test that I gave a couple years ago, which will be similar to the one I'm doing now, but not quite, especially because there's different chapter material. Okay. So last two slides. This is an empirical formula problem looking at what is the empirical formula for 100 grams of compound containing 23.5% oxygen, 70.6% carbon, and 5.9% hydrogen. So what is the empirical formula? In a situation like this, we're going to turn percent to grams, and then we're going to turn grams to moles, and then we're going to do mole ratio. So I'm just writing this down on my little sheet, and then we're going to go to the .chem. So .chem. Now, because we have 100 grams, but you can always do this regardless of whether you do 100 grams, is you can make the assumption of 100 grams because whatever amount you use, it's going to be the same for all of it. So if you did 200 grams, you're going to get the same numbers. Everything's going to be doubled. So you're going to get the same ratio. So it's possible to just say, assume 100 grams. Any percent times 100 grams is going to make this 23.5 goes to 23.5 grams of oxygen. That's going to make 70.6 grams of carbon. And it's going to make 5.9 grams of hydrogen. Now, to get a mole ratio, we have to turn these guys into moles. In order to turn these into moles, we need the molar mass. Oxygen, looking at the periodic table, is 16 grams in 1 mole. Carbon, 12 grams in 1 mole. And hydrogen, well, it's essentially 1 gram in 1 mole. It's not perfect, but this will work to get us close enough. So 5.9 moles of hydrogen. 23.5 divided by 16 is 1.47 moles of oxygen. And 70.6 divided by 12 is 5.89. Essentially, or 5.88. Essentially 5.9. Now, to get the mole ratio, we're going to take the moles of each one and divide by the lowest amount. So we're going to divide 5.9 by 1.47, 5.8 by 1.47, and 1.47 by 1.47. Get what is the ratio of hydrogen, carbon to oxygen? So 5.88 divided by 1.47 is 4.00. Pretty safe to say that's 4. 5.9 divided by 1.47 is going to be essentially 4. 4.01, that's also essentially 4. So our empirical formula, which is the simplest whole number ratio of these 3 mole ratios, is C4H4O1. We're looking at the simplest whole number ratio between these 3 atoms. So what did I do? I turned percent mass to grams. I turned grams to moles, and then I just found the simplest whole number ratio of moles to moles. So the only real part that's different from any other math problem in this chapter, is moles to moles. It's the mole ratio. Now, all that's well and good. All that's well and good. So, but the empirical formula is not always the empirical formula is not always the molecular formula. The empirical formula is simplest whole number ratio. You could have a molecule that's C4H4O, but you could also have a molecule that has more oxygens than that. You could have C8H8O2. You could have any ratio. And so what we're going to look at is the molecular formula. Now, I have a quick note up here. If the mole ratio is not close to a whole number, don't just round it, especially if it's an obvious fraction. 1.5 to 1. 1.5, typically in math, we would round that up to 2. But 1.5 is pretty close to a 3/2 ratio. Unless our math is really, really bad, you should get it somewhat close to a whole number. So 1.5 to 1 is close to a 3:2 ratio. 1 1/3, which is 1.33 repeating, is close to 1/3. So you can go 1.33 is a 4:3 ratio. Sometimes you will have 4:3 ratios, and so we don't want to round unnecessarily. If it's 1.1 or 1.05, yeah, you could probably round that down. If it's like 1.8, 1.9, you could probably round that up. But if it's like 1 1/3, 1 1/2, you may not actually want to round that. But okay, so the molecular formula. Once we have the empirical formula, how do we find the molecular formula? In order to do this, we have to know the molar mass. And there are various ways of determining the molar mass. The molar mass can be found by looking at the melting point, which has a strong dependence on the molar mass. You could use what's called mass spectrometry, which is an organic spectroscopy technique that finds the molar mass of things, among other properties. But basically, once you have the molar mass, what are we going to do? we're going to look at our empirical formula and compare our empirical formula mass to the molar mass. If done right, the empirical formula should be some factor of the molar mass. It would be some factor. Oxalic acid would have a molar mass of 90 grams per mole. The empirical formula of oxalic acid is H1C1O2. If I look at the molar mass of H1C1O2, hydrogen is 1, carbon is 12, oxygen is 16, and there's 2 oxygens, so 32. 32 plus 12 is 44. 44 plus 1 is 45. So a molar mass of 90 is evenly divisible by 45 for 2 times. So that means there are 2 fragments of the empirical formula in that molecular formula. If there's 2 fragments, that means we'd have to double the empirical formula. Looking at our example we just did, the C4H4O1, that has a mass of 12 times 4 plus 4 times 1 plus 16. So that fragment has a molar mass of 68. If the molar mass of that whole compound is 68, the empirical formula matches the molecular formula. If the molar mass of the whole compound is instead 136, we would have to double everything. If it was 204, we would have to triple everything. And that basically, the molar mass of that C4H4O fragment is going to be some factor of the actual molar mass. And we can figure out everything about the compound from there. That is the last slide. That's the last slide. So we're going to jump straight to looking at the old test. I need to pull that up. Okay. I just posted this on like over the weekend. So it's new if you haven't. You look, so test 1 practice. This includes 2 actual tests. So you can feel free to download these, whatever these are. This was the test I gave last year and one I gave fall of 18. But that was a take-home exam. So let's just look at what I gave. This one more closely resembles the material we're dealing with right now, because this goes chapters 1 through 3. The other one, it will more resemble the type of the test questions, but this one is more resembling the question material. So we'll see here we have a variety of naming. We'll go through each of these in turn, take our sweet time. So we may not get all the same types of questions, but we get some similar ones. You notice I'm going to reuse these useful information down here on the take-home test, though technically, since this test is posted online, you have access to this. You don't need me to give you this because you already have it. But inches to centimeters, feet to inches, feet to yards, feet to miles, kilometers to miles. These are all present here, but you could also look them up on a take-home test. I give you Avogadro's number and I give you the units. There's actually a few more equations that I could give you, like density, grams to moles, all that stuff. You need to be able to use that. Well, okay, starting with number 1. Using the metric ruler, measure the bolt in centimeters to the proper number of digits. The idea here is just a significant figure problem. This is something you should have learned in lab. Basically that you measure to the correct number of dashes and you measure one past at the estimation point. If this is measuring in centimeters, so this is definitely 3 centimeters. The smaller dashes are in millimeters. Smaller dashes are in millimeters, so it's 3.2. And if we look here very carefully, it's somewhere between 2 and 3. The place between 2 and 3 millimeters means it is the estimation point. So here's where there's a little bit of fudge factor. There, you could say it's, depending on how well you look at that, that's 3.4, 3.24. Maybe you're going to say 3.23. I'm willing to accept a variety of answers as long as it's not too outrageous. Is it closer to the 2 or is it closer to the 3? I'm going to leave it up to you, but you should have reported something 3.2 something. And the idea is you always measure to the estimation point, which is the point between the markings. So whenever you're measuring something that has markings like that, and it's not a digital scale or anything like that, that's how we're supposed to measure these things. Number 2 is a conversion problem. Back when we used to be able to travel, we went to Ireland. Remember when I used to be able to travel? Also, the car got 15.7 kilometers per liter. What is the fuel efficiency in miles per gallon? So it's just a simple conversion, 15.7 km per L. Now I'm going to scroll down and grab the units. So grabbing those units down there, I'm going to set that up 1.609 km per 1 mile. And then the next unit, that 3.875 liters in 1 gallon. So pulling to the dock cam real quick. So notice I set up 15.7 kilometers over 1 liter. And it doesn't matter which order I do this step in, as long as I do both steps. I said, since this is kilometers over here, I need kilometers down here. So kilometers and kilometers cancel. So I'm going to take my 15.7 divided by my 1.609. And now I need to get liters into gallons. So I have liter down here, so I need liter up here. I set this up so that liters cancel and kilometers cancel, so that they're on opposite sides of this. So I'm going to multiply by 3.875, and that would give us a fuel efficiency of 37.8 miles over gallons. 37.8. Now, keep in mind here, 37.8. If I were to have to report this to the correct number of sig figs, it would indeed be 37.8. Why 37.8? Well, it comes down to the fact that the original number, 15.7, is reported to 3 sig figs. The conversion factors are all 4 or more. Conversion factors are all 4 or more, meaning that the first number I gave you is the number that controls everything else. So 37.8 is the correct answer. Sheesh, where's the mouse? Okay. What is the following compounds? Spelling count. So Now on a test, a take-home test, I'm going to ask you a little bit more in depth because I've learned the first time I gave this, people just Google. And sure, I guess you can still just Google the name, plug them in and hope for the best. But I want you to take one step further. Like you should be able to explain what type of compound this is and use that behind what you're doing this. So like, what are the charges? Would you put this together? So I would say this is a molecular compound, and I'd call it boron trifluoride because there's moleculars named with the prefix. N2O, also a molecular compound, so we'd call that dinitrogen monoxide. Describe in your own words, 2 to 3 sentences, the result of Rutherford's gold foil experiment. So, there's an explanation one, basically just use your own words. You'd be like, blah, blah, blah. Rutherford, they shot gold foil with alpha particles. They expected the alpha particles to punch through and prove the plum pudding model. It rejected that, and we saw the nuclear model because we have a dense nucleus ricocheted off the atoms. Number 5. How many atoms of phosphorus are in the structure? 35 moles of P4O10. 35.0 moles P4O10. So don't mistake this one. This one is actually one step harder. It's not just moles to molecules, it's also molecules to atoms. We have to be able to first turn to molecules using Avogadro's number. 1 mole, 6.022 times 10 to the 23rd molecules. But I ask you, how many phosphorus? Well, in the structure, just like in the homework, in the structure there is 4 phosphoruses per P4O10. In 1 molecule of P4O10, there is 4 atoms of P. So what do I have to do? I have to do 35 times my 6.022 times 10 to the 23rd is 4. Make sure you're not, like I almost did, raising that 4 to the 23rd power. Or not 10 to the 23rd times 4. You should get something like 8.43 times 10 to the 25th. That 10 to the 23 is simply kind of pulled out. And so you essentially get 35 times 6 times 4, you get 840. That 840 is a factor of 2, which just adds to the 25. So the correct answer is 8.42 times 10 to the 25th. Right there. Answer C. Copper has a major isotope, 62.93 and 64.927. Essentially, if copper 63 has an isotopic abundance of 69.15 and copper of 30.85, set up the equation to solve for the average weight and determine the atomic weight up to 2 decimal places. So this one looks and sounds hard, but the weighted average is not actually that hard. All said and done, it just becomes mass times percent. 295,975 times 0.6915 plus 64.92778895 times 0.3085. Once again, there's a lot of going back and forth to the doc cam because to show the work. So I'm simply taking mass times percent, mass times percent, and I'm adding them up, and I need to do it to 2 decimal places. So 295976915. So don't think this that hard. It's just remembering how to approach this. Once again, in the example of a take-home exam, you have time to look this up. You have time to go, hey, crap, I don't remember how to do this. Is there a homework problem like this that I can learn how to do it? Yes, there's at least 2 on chapter 2. You could probably come back to this problem. But so I did the math, I added them up. So the mass of copper should be 63.55. 63.55. I rounded to 2 decimal places. Calculate the force of an elephant falling on you, rounded to the correct numbers of an elephant. Okay, this is one of those. I think I actually need to open with the part of this. I'm going to skip part of this test because some of this, what you may have to do is open this with Word. This is one issue we will have consistently, is that I will put equations in Chem Editor. I mean, not in Chem Editor, but like equation editor. Word will open them just fine. However, when they are displayed through Google Classroom, any equations, any numbers that are put in the equation editor software will be deleted out. They'll just disappear. So you may have to download this to look at those, which is why when I send you the test, it will be as a PDF rather than a Word document. If I had saved these as a PDF and uploaded it, they should be just fine. So there may actually be some equations that have disappeared. So we'll go ahead and skip that one. We're not going to worry about that one either way. Not a question that really needs to be answered. Whether following properties of lithium as chemical or physical. Just remembering the first little bit of chapter 1. Density, light enough to float on water, would be a physical property. So remember, physical properties can be measured without changing the identity of it. Change from silver to black in moist air. So that's physically oxidizing. It's reacting with the air. So that's a chemical property. Burns in oxygen. That would be a chemical reaction. Can be cut with a knife. It's physical. You're not actually reacting it. You're just separating atoms from other atoms. Here's one closer to what we will see. Find the proton, neutron, electron count of silver 108 positive. Silver 108 positive. So silver 108 positive. So the first thing we need to look up in this type of thing is what is the proton count of silver? We can find that directly from the periodic table. In this particular situation, I did not give you this because I know you can do this on your own. You can you have a periodic table, you can look it up. Okay, so that up. Silver going down is 47. So that's our first number. Our proton count is 47. Our neutron count is the sum of 47 plus the neutrons is 108. Here's where you can't just grab something from the table. Yes, this one, the average mass, you can't really see it, is 107.88. So close to 108. But I'm not going to always use the most stable isotope. So you can't just grab, if I grab carbon 13, you can't just grab, oh, carbon 12 is 6 and 6. Well, carbon 13 would be 6 and 7. But neutron count. So 108 minus 47 puts us at 61. And electron count. The electron count is comparing the charge to the proton count. Because protons minus electrons will give us the charge. So positive 1 means we have to have one less electron than we have protons. So 47 minus 46 would give us a positive 1 charge. Neutron. Protons plus the neutrons give us the atomic mass. Protons minus electrons give us the charge number. So 40, 47, 61, 46. Be able to do that with ease. That should be easy points. That should be easy points. What is the molecular formula of aluminum bromide? So this one you kind of have to, since it's a multiple choice, you can guess, but on a take-home test, how I have this. So I say aluminum bromide. Aluminum bromide would be an ionic compound. Aluminum bromide is not transition metal, so it's going to be aluminum 3 plus, bromide 1 minus. So I'd ask you that, and then finally you put it together. Well, if that's 3 plus and the other one's 1 minus, you have to have 3 negatives to cancel 1 3 positive. So you would have to have aluminum AlBr3. I can't really read my little squigglies. They're a little small. It might be A, it might be C. I'd have to double check. It doesn't really matter. But the AlBr3. Determine the molar mass of zinc sulfate. Zinc sulfate, you're just going to have to find what is the mass of each component, add them up. And so zinc, pulling that up. If I'm not mistaken, zinc is 65.4. We'll pull that up just to make sure. Zinc is 65.4 or 65.38. Plus sulfur, which is 32. Plus oxygen, which is 16. And we have to multiply by 4. 16 times 4 plus 32 plus 65.4 gives us 161.4 grams per mole. So I may not ask you an individual question of this, but you will still have to do this process. Because anytime you're turning grams to moles or moles to grams, you're probably going to need to find out the molar mass. Okay, now where's, oh, shoot. Okay. Okay. Just expect at least one lab-like problem. So if you haven't done lab 1, get with someone who has. Make up do the lab sometime before next week. It's not super hard, but look at it. So we're figuring out density. This 1. Say, determine the density of antifreeze at empty beakers weighed. The empty beaker, so the tare mass is 35.215. We add about 10 mils, 10.00 mils, and the total mass is 46.351. And they want to know what is the density of antifreeze to the correct number of significant digits. Well, I say they, but me. I do. I want you to find that. Okay. So the first thing is, in this particular situation, you subtract the tare mass from the total mass to figure out what is the mass of antifreeze. So I get 11.1136. I keep all those digits because I'm rounding at the last sig fig when I multiply, when I subtract. Now to get density, I take that mass and I divide by my number 10.00 mils. Now this one has 1, 2, 3, 4, 5 sig figs. This one has 1, 2, 3, 4 sig figs. So when I report this number, 1.114, I must round to 1, 2, 3, 4 sig figs. Because when multiplying or dividing, I keep the lowest number of sig figs. When adding and subtracting, I keep the position of the sig figs. So pull that back up. What is the compound with the formula MgSO4? So MgSO4 would be magnesium sulfate. But so what did we do? You first should say, oh, it is ionic. 2, I would ask you on a take-home test, Mg is 2 plus, SO4 is 2 minus. So it goes together in a 1-to-1 ratio. And you might need to answer, son, it is not a transition metal, so we don't need the number. So it's just magnesium sulfate. SO4 is what? If it's SO3, if it's SO3, I can't reread my own thing. If it's SO3, it'd be magnesium sulfite. If it's MgSO4, it's sulfate. If it's MgSO3, it's sulfite. SO4 is our base. To remove 1 oxygen means I change it from 8 to 8. Obviously, we can't do 14 without opening this up in Word, and I'm not going to deal with that. It's basically a sig fig number, and I'm not going to throw a straight up sig fig one. I'm going to ask you to report numbers to the correct number of sig figs. What is the molecular formula of iodine heptafluoride? Iodine heptafluoride. It's a molecular compound, so we name it like a molecular compound. Iodine, it's going to be 1. Hepta means 7, so it would be IF7, which is C. IF7. Okay. Based on the position on the table, determine the expected properties of the following element, mercury. Turns out mercury is a liquid, but you might expect it to be a solid. It's in a transition metal, so it's an electrical conductor. It's a transition metal, so it's a thermal conductor. It's a metal, so it's lustrous or shiny. The only thing that should really trick you is the liquid part. Determine the names of the following acids. So there's an option for the acid. H is always +1. I is always -1. I is -1. Now, because it's like a monoatomic acid, we call it hydroiodic. iodic acid. Now, HNO3, it's not a monoatomic. It's not just N. It's NO3. So we go from, there's no hydro. It's just nitric acid because the 8 goes to ic. 2 more problems. Well, actually, maybe, yeah, 3 more problems. Determine the moles in 652 grams of calcium carbonate. So 652 grams of calcium carbonate. So this one shouldn't be too bad, but you have to look it up. Calcium is 40. Carbon is 12. Oxygen is 16 times 3. So 40 times 12 times 16 times 3. Oh, sorry, 40 plus 12 plus 16 times 3. So the molar mass is 100 grams in a mole. I'm just looking back real quick. Okay, they're asking the number of moles. So literally, to do this, we're taking 652 grams with 100 grams in 1 mole. So how many moles? 6.52 moles. All I'm doing is set up grams top, divide by grams to get just moles. Just moles. One more math problem. Walter Payton, famous running back of the 1986 Chicago Bears, could run 40 yards in 4.58 seconds. How fast is that in miles per hour? 40 yards in 4.58 seconds. So I'm setting up that initial ratio, and I want to go to miles an hour. And before you ask, no, is that necessarily, is he the fastest? Oh, God, no. But he's relatively famous, at least if you're from Chicago or Illinois. So I'm going to go from yards to feet to miles. So in 1 yard, there is 3 feet. And in 1 mile, God, I can't remember this conversion. Let's see. Kind of embarrassing. But oh my God, I gave him way too many problems on this. I thought I was almost done. They're 5,280. 5,280. 5,280 feet. And there's 60 seconds in a minute and 60 minutes and 1 hour. So I've set that up so that yards cancel yards, feet cancel feet, seconds cancel seconds, minutes cancel minutes. The only units we have left are in miles per hour. So 40 divided by 4.58 is our first ratio. Times 3 times 60 times 60 divided by 5,280 puts us at 17.9 miles an hour. So, A. What are the names of the following compounds? Spelling counts. I'll do these naming one and maybe skip to one last problem here. And then on Wednesday, we'll look at the take-home test ever so briefly. Well, at least a bit of it. So don't feel like I'm going to throw you into this without at least looking at what the take-home test would entail. But okay, iron. I think it's FeCl2 if I'm reading that right. Ions aren't what they used to be, but FeCl2. You would write ionic. It's a transition metal, so it's one of those weird ones. So we have to look where chlorine is. If chlorine is 1 minus and there's 2 chlorines, iron has to be 2 plus. So you say ionic, iron 2 plus, chlorine 1 minus. So when you name this, it would be iron 2 chloride. MgO, it's ionic. Mg is 2 plus, O is 2 minus, so it's just, but Mg is in column 2, so it's magnesium oxide. Don't need any fanciness on there. Be able to do this as well. So instead of going proton, neutron, electron, be able to go neutron, electron, proton. Go from one way to the other. Let's see, Death Valley, blah, blah, blah. I'm going to skip 23. Okay. We'll do 20. Oh, God, how are we doing? We can do 22 and 25 real quick. 22. What is the mass percent of oxygen and magnesium hydroxide? So in this case, you figure out in magnesium hydroxide, what's the mass percent? You find out how much mass is magnesium, how much mass is, well, how much mass of oxygen versus how much mass total. So magnesium hydroxide, MgOH2. So the total mass is 24.3 from magnesium plus 2 oxygens plus 2 hydrogens. So 32 plus 2 plus 24.3. The total mass is 58.3. The oxygens account for 32 of that, 16 times 2. So to get the total mass, the mass percent, you're going to take 32 times 58.3 times 100, because mass percent is individual divided by total times 100. So oxygen is 32 of that 58. Your mass percent should be something like 54.9%. 54.9%, which is D. And the last one I cover is 25. Determine the empirical formula of a thing with 7.7% hydrogen, 92.3% carbon, and a molar mass of 78. And I just want, what is the empirical formula first, and then bonus points if you can get the molecular formula. So to finish off, I've already converted percent to grams. We're going to just assume 100 grams. So dividing 7.7 by 1 gram and 1 mole gives us 7.7 moles of hydrogen. 92.3 divided by 12 grams per 1 mole. So how many is 7.69, which is essentially 7.7 moles of carbon. If I have a 7.7 and a 7.7, what is the simplest whole number ratio between the two? 1 to 1. So what is the empirical formula? C1H1. Now for the bonus points, that fragment weighs 12 plus 1, or 13. 13 grams per mole. How many times does 13 go into 78? 78 divided by 13 is 6. So what is the molecular formula? C6H6. So that's all the time we have for today. On Wednesday, we will look at the take-home exam. How does that differ? The basic idea is like the problems are a little bit more complex, maybe a little bit more laid out, but you definitely do the same work. You show your work, you state your answer, and that's what I'll go over on Wednesday before starting any new material. Have a good day.